When you see a proton spectrum worked up and you see how much information is contained within that spectrum, there's no surprise that a table describing that spectrum likewise contains a lot of information. And specifically, if you are looking at a worked up spectrum, the integration, the most important information, is contained down here, but you also have chemical shift information up at the top, and of course, there's multiplicity information, which you can tell by looking at the peaks, and if you are good, you can use the information up here to extract the J values. So the table describing all of the information in a Proton NMR includes all of those elements. Integration, which again I consider the most important. Chemical shift, second most important. Multiplicity then is the least important of the three main ones, but the J values then help you figure out which peaks are connected to which. And the only one that you can't read off a worked up spectrum kind of at a glance is the J values. And you either have to do a little bit of math using these tiny little values, or ideally you go and you work up the actual spectrum again and do the measurements with something like the crosshair tool as illustrated here, so dragging from one peak to another. By contrast, a C13 spectrum just contains massively less information. A table describing a C13 contains only chemical shift. Why don't we perform integration? Why are these singlets as opposed to multiplets? The answer to that is that these are deliberate choices that we have made. We could instead do other things, but we don't. And we do that for very good reason. This video is about why. So let's consider the carbon NMR spectrum of ethyl acetate. We have a carbonyl, which has a chemical shift expected of around 170 or so, particularly because this carbonyl is of the ester type as opposed to the aldehyde or ketone type, which you might expect to be around 200. We also have a carbon that's next to an oxygen. It's alpha to an oxygen, so you might expect that to be in the rough 60 to 90 parts per million. There's a plain boring methyl, which will be in the 10 to 20 range, and then there's a methyl that's attached to a carbonyl, which should be to the left of the plain boring methyl. If we go to open a C13 decoupled spectrum, this will show you what you are used to seeing. Said another way, there are four main peaks for the compound. There is, of course, still CdCl3 or whatever solvent is present, and you know that you have to set this as a reference. The midpoint of it is 77.16. Zooming out, there does not appear to be any TMS, so the midpoint of CdCl3 is the correct place. And again, we expected to see four signals for the carbons. There is a carbon that's in the neighborhood of 170, a carbon in the neighborhood of 60, a carbon in the neighborhood of 21, and one in the neighborhood of 14. Therefore, A, B, C, and D in order. And so you might wonder to yourself, why don't we perform integration in a C13? Looking at this ChemDraw image, what you see is that there are four carbons, each in their own unique environments. Therefore, if we were to integrate them, we might expect them all to have an integration of approximately 1. And in fact, if you just simply highlight ethyl acetate itself and you ask ChemDraw to perform a C13 prediction, what you will find is that ChemDraw will predict that there are in fact four different carbons, and it will predict them all to have the same height, the same intensity, which is a pretty good proxy for integration. And by the way, ChemDraw predicts 170.2, 61, 20.7, and 14.1, indicating that ChemDraw is pretty decent for C13 predictions. But in practice, that's not what happened when you go and work these up. You can tell that just by looking at the relative heights of these. Now, height alone is not a great indicator because area under the curve is given not only by the height of the peak, but also by the width of the peak. So it's possible that this could be a short and wide peak. But in practice, a peak that has no hydrogens bound to it is going to show up as extra small in the C13 NMR. But here, all three of these peaks should be identical in height, or at least identical in area, and in practice, they won't be. So if we simply do integration from left to right, trying to be relatively mindful of not including very much of the baseline, because the baseline in a C13 is relatively noisy, then what you'll find is that these peaks do not integrate for all 1 each. This carbon, the carbonyl, if you integrate that for 1, then yields very different results for all of the others. So we can't trust the integration in a carbon. And the main reason why you can't trust the integration in a carbon is because of how noisy the baseline is. It's very difficult to get just the peak itself. But I could solve that by zooming in more and only getting the peak itself. That being said, there are other issues at play here as well. But again, even looking at these three that contain hydrogens bound, so this is the carbonyl carbon, it does not contain a hydrogen bound to it. All of the other three are more similar to each other than not. 3 hydrogens bound, 2 hydrogens bound, 3 hydrogens bound. If you look at the C13 spectrum, all the ones that have hydrogens bound are much larger than the carbonyl carbon, but also they end up as quite different than each other if you try to do the integration. So the overall message is you cannot trust the integrals, at least in part because of the baseline issue, but at least in part because each of the carbons relaxes at a different time, and it just takes a lot longer for the carbon to relax back into the ground state if it has no H's bound versus the others. That's not the only thing that's going on either, but it is a main reason. But the overall message is you cannot perform the integration. It just does not work. Returning now to the image of ethyl acetate, what I have done is draw in all of the explicit hydrogens for the molecule. And the main reason why I've done that is to illustrate how many hydrogens are bound to each carbon. A does not have any hydrogens bound, whereas B has 2 hydrogens bound, C and D each have 3 hydrogens bound. And this is relevant because a carbon and a hydrogen are both spin 1/2 and can couple to each other. In other words, this carbon is going to be affected by the 3 hydrogens bound. And if we collected the spectrum without turning off that information, what you would see is a quartet, because of the n+1 rule. If you look at B with 2 hydrogens bound, you would expect it to be a triplet, again according to the n+1 rule, and D would likewise you would expect to be a quartet because of the n+1 rule. In a standard C13 spectrum, of course, we have just the 4 singlets. If we now do the carbon coupled spectrum, what you see is that the carbonyl is still a singlet. We still have CDCl3, and then we have triplet next to the oxygen and 2 quartets. Returning to the decoupled spectrum, which is to say removing that hydrogen information, what you consider to be the normal spectrum, I will now remove the integrals. This is because I want you to focus now entirely on where these peaks are and how tall they are. Here, if I go and use the manual zoom function and set this to be -200 to 2000, we can now do the same thing for this spectrum as well. And the key point I want to make to you is that I have not changed anything at all about the sample. The compound is identical in both of these. I just collected them via 2 different pulse sequences, which means that the CDCl3, which has no hydrogens, is unaffected by the 2 experiments that I have run, and its intensity shows up at approximately 550 in both, roughly 550, 600, and same thing. And what you notice now is because these are all singlets, they are much taller. We get up to nearly 1900 over here, and the carbonyl is about 500, whereas if you look at the coupled spectrum where you have quartets and triplets and singlets, then everything's much smaller. This is nearly 5 times lower, and this is likewise about 5 times lower, and so there is a dramatically worse signal to noise. It is much easier to see singlets in the spectrum than it is to see the coupling information. Now, you lose some information when you do this, of course. It is useful to know that there are 2 hydrogens bound here, and there are 3 hydrogens bound to each of these. But we can gain that information back in a different way, and we do not need to run the pulse sequence this way in order to get that information. And so, in practice, it just proves to be much easier and simpler and better to collect carbon NMR this way. Putting both spectra on common axis, I think, really illustrates that these peaks are just much taller relative to the CDCl3 rather than these. And again, you could choose to collect it any way you want, but in practice, this is much more useful, especially because of how long it takes to collect C13 spectra. A standard proton NMR can be collected in about 50 seconds. 8 scans is more than enough in order to see all of your proton information, whereas a C13, you usually need 64 scans, 128 scans, 1024 scans, and so we're talking about 5-minute, 10-minute, hour-long experiments instead of 45 seconds. And so in practice, we just choose to collect the C13 spectra this way, and we get the information more effectively sooner. One last thing I want to illustrate for you here by changing the zoom is that you can see that the peaks end up in the identical location in both cases. So our triplet, this singlet now ends up at the center line of that triplet. The singlet ends up again directly in the middle of this quartet. This singlet ends up directly in the middle of this quartet, and so on. So the peak location is identical no matter how many lines the peak has. It's just, again, in practice, better to collect this information that allows us to plot the C13 spectra as singlets as opposed to multiplets. Why do we only collect chemical shift? Well, because practically chemical shift is the information that's valuable to us that's reproducible. You could collect integration information, but unfortunately it's not very reliable. To some extent, intensity is a proxy for integration, but again, carbonyl carbons, carbons without hydrogens bound, will tend to be smaller than all others, and the intensity information is not perfect anyway. So we tend not to collect integration information because it's not as reliable as we'd like. For multiplicity, we prefer not to collect it because the signal to noise is better. And if we're not going to have multiplicity, if everything's going to be a singlet, then obviously there are no J values at all.